Let us now discuss some topologies for PV grid interface. There are many topologies available in the literature. They probably may be classified in the following way. One of the main classifiers would be isolation. There are many topologies based on isolation, where one places the isolation and whether isolation is needed or not. So you will find low frequency transformers being used for isolation, high frequency transformers being used for isolation. You will also find circuits without transformer isolation. They are called transformerless PV grid interface. Each have their pros and cons. We will discuss them. There is also classification based on the number of power stages. So you see, you may have one power stage, one DC-DC converter to take care of maximum power point tracking for the PV modules, source modules. There is another DC-DC converter which can be used for current control or voltage control of the output. There can be another converter for doing the unfolding. So if you will see that there are some topologies which uses 2 or 3 converter stages. Some topologies which will use just one power converter stage. So it has an impact on the efficiency of the whole system. So you will see in the literature topologies based on the number of power stages too. You will also see converters based on control dynamics. So you will see scalar control, where the control is done intercycle with intercycle dynamics. That is, it may take more than 150 Hz cycle for the dynamics to settle. If you use the DQ axis theory, then you will obtain intracycle dynamics. That is, the dynamics will settle within a cycle. So these are control blocks which are which are popular and which are in use, and we shall also discuss some of these things while designing or while even looking at the PV grid interface circuits. So one by one, let me introduce the different types of PV grid interface circuits, and let us spend some time discussing them. Let me take up the following topology, where we have the PV module connected to a DC-DC converter, and the DC-DC converter output has a capacitance. DC-DC converter has a control input like this, and this control input is used for MPPT control. Now this portion we are familiar with. You have the buffer capacitor CT, DC-DC converter, and an output capacitance. What we want to do here, I will discuss. Up to this portion we know, and this DC-DC converter can be any DC-DC converter, either non-isolated or isolated, which will appropriately do the matching of the load line to the PV terminals in such a way that maximum power is drawn from the PV. The output of this DC-DC converter is given to input of another DC-DC converter. So the job of this other DC-DC converter is to control the output voltage on the downstream side. The job of this DC-DC converter was supposed to control the input impedance for maximum power point tracking. So each of these DC-DC converters is doing different functions. So output of this DC-DC converter is supposed to give an output which is unidirectional. It is still DC, but it is a varying DC, and the variation is such that it is in the shape of rectified sine wave. So you can control the duty cycle of this DC-DC converter in a way which will give you an output which is giving you rectified sine wave. The output of that DC-DC converter will go through an unfolding circuit. I'll call this one as an unfolding circuit, and what it does is alternately it will unfold this full rectified sinusoid, so that you will get a sinusoidal wave shape at its output. So job of the unfolding circuit will be such that it will provide the positive, first positive will still remain positive, the second rectified sign will become inverted, so that together it becomes a sine wave. Now this sine wave will be passed through an isolation, transformer isolation, low frequency, because this is at now 50 Hertz. So you will use a low frequency transformer isolator, and an output of that is going through an inductor, and that will get connected to line and neutral of the grid. Observe that this DC-DC converter is also having a control input, but this control input is used for modulating the output voltage of this. Can be used for voltage control or current control. We are quite familiar with this portion of the circuit. We know how to interface the PV module with the DC-DC converter for MPPT control. Let me discuss about this portion of the circuit. Now let me put down a typical circuit for this portion. Starting from this capacitance onwards, let me redraw the circuit here. So I have the capacitance. Let me follow it up with a simple buck converter like this. So this is a buck converter. So I have a power semiconductor switch. Here I have used a BJT. You may use a MOSFET or you may use an IGBT. Have the diode, and you have an inductor and the capacitance. Now you should remember that this portion, what I have used this topology of a buck converter. You may use any other DC-DC converter topology. This is just only a representative topology. For explanation, I have used a buck converter. It could be a flyback converter, it could be an isolated converter, it could be a buck boost converter, so on and so forth. It could be a Z source converter. Now the output of this should have a wave shape like this, full wave rectified, sine rectified. So appropriately I will have to give a duty cycle here which is varying such that it will produce an output wave shape in that fashion. Now the output of this, I will give it to a push-pull converter which is connected in this fashion. Now I have this transformer winding, and this is a push-pull circuit. So recognize this push-pull circuit. There is a switch here, there is a switch here. I have not put a diode here purposely because this reverse body diode is used if the current flow direction reverses, but we are talking of pumping in current always in phase with the grid. So it is only the active portion of the power which is flowing through always. Therefore I have not put a reverse diode, but you may put a reverse diode. If it is a BJT or if it is a MOSFET and IGBT, the reverse diode is already inbuilt within the body of the switch. So now this voltage output coming from the DC-DC converter, this DC-DC converter is now connected to the center point of the push-pull transformer. The secondary of the push-pull transformer is passed through an inductor, and output of that connected to the grid line and neutral as shown here. So now this duty cycle here, I will modulate this duty cycle in a sine fashion such that at this point the output I will get a voltage in this fashion. You see this V0 for a buck converter, V0 is equal to D times V in. Now if D is made sinusoidal in nature, that is only rectified sinusoidal in nature, you will get an output V0 which is V in sine of omega t, and therefore you will be able to get this kind of a wave shape. Now this kind of a wave shape is given to the center of the push-pull. Now let us say this half sinusoids are having 10 millisecond width. So two sinusoids, two half rectified sine waves will make 20 milliseconds, which is 50 hertz. Now we will unfold this. So what I will do, this is Q1. I will switch on Q1. So which means during Q1, this is the operative sinusoid, half sinusoid, and the dots, observe the dots here, and I'm supposed to get this. So when this is switched on, this dot is positive, this dot is positive, dot is positive, so the positive comes in here. Now when Q2 is switched on, Q1 is off. So this is the Q2 portion. So when Q2 is switched on, non-dot end is positive, non-dot end is positive, non-dot end is positive, which means dot end is negative. This is the portion, it gets inverted like this. So alternately you keep switching Q1 and Q2. So these are switched in the 50 hertz fashion. For 10 milliseconds this is on, next 10 milliseconds this is on. So these are switched at low frequency. And this unfolding happens, and then this 50 hertz signal is now interfaced to the grid through the inductor. So this is one way of interfacing. This portion is called the unfolding circuit that I mentioned here, and this is the unfolding circuit, and this portion is the isolation. The push-pull transformer is used for isolating. So this and this portion is what is actually indicated in this whole circuit. This is one such topology here. The unfolding stage here I have indicated using push-pull stage, Q1 and Q2 along with a push-pull transformer. This unfolding stage can be replaced with a bridge circuit, which is much more popular because the bridge stage is decoupled from the isolating stage. Here the push-pull stage is tightly coupled with the isolating stage. So let us have a look at that. What I will do, I will remove this portion of the circuit and redraw that. Let me reduce this, and here I will use a full bridge stage which is switched at low frequency. This time instead of using a BJT, I will draw a MOSFET as the power switch. See the MOSFET, this is a N-channel MOSFET with the internal body diode. You see why I normally use a BJT for switches representing the power semiconductor switches. It is much easier to draw a BJT than draw the power MOSFET. But when I use in the lab and experiments, most of the time it is always power MOSFETs and power IGBTs. Very rarely I use BJTs. Okay, so we have this full bridge made of power MOSFETs. This is connected to ground, this point, and this center point of this one is connected to this point, which is actually getting the full wave rectified sine power signals. So I will connect it like that, and then the center of the bridge I will connect a transformer like this, and the output of the transformer, secondary of the transformer, goes through an inductor and then to the line and neutral of the grid. So let me complete this internal body diodes of the MOSFETs. So you have the body diodes, the MOSFET, complete dot polarities. So this would be the complete circuit. Let me now name the switches. I will call this one as switch S1, this is S2, this is S3 and S4. Now let us say during this period let switch S3 and S2 be connected. S2 and S3 be on, S1 and S4 are off during this 10 millisecond period here. So during that time, this dot end of the transformer is connected to the positive of this DC-DC converter. The non-dot end is connected to the negative of the DC-DC converter. So the dot end is positive, this dot end is positive, and therefore you will see this portion appearing here. Then for the next 10 milliseconds, I will switch on S1 and S4, switch off S3 and S2. S1 and S4 are switched off, S3 and S2 are switched off. So when S1 and S4 are on, you will see that the non-dot end is connected to the positive of the DC-DC converter. The dot end is connected to the negative of the DC-DC converter. Therefore, the dot end is negative. So you will see an inversion here. You see a full sine wave appearing across the primary and the secondary of the transformer. The primary and secondary turns ratio, the turns ratio is decided depending upon whatever this voltage of the DC-DC converter and whatever the voltage would be of the grid. And in India, this grid voltage is 230 volt RMS or 325 sin omega t. So you can adjust this ratio to match the grid voltage.